Welcome everyone to this lunch seminar that we will have today, and I'm very pleased that we have Gustaf Hugelius from the Stockholm University. He is at the Department of Physical Geography at the Stockholm University. He also is a co-director of the Bolin Center for Climate Research, and together with Ilona Riiponen. And I will also say that a news that coming before Christmas, that Gustaf is among the world's most scientists in his research field. This is actually amazing. So the title of the Gustaf talk here today is Thawing Permafrost Affects the Global Climate, How It Does It, on the climate and ecosystem, and also, of course, of Arctic peoples. So please, Gustaf, start.
Thank you very much, Paul, for that kind introduction, and thank you for inviting me to give this talk, and thank you to all of you that are listening. So I hope that you see my slides well, and then just let me know if there's some problems with seeing that. So I will talk, as Paul mentioned, I will talk about permafrost thaw, and its role in the global climate or the global carbon cycle. And with that said, I actually want to start with a graph showing us the global carbon cycle, because I feel like that we need a bit of a background or primer to the carbon cycle to understand the role of permafrost sort of in this global context. So throughout the presentation, whenever I mention stocks or amounts of carbon, I'm talking about the stocks of carbon themselves. So if you want to translate between carbon and CO2, then 1 gigaton or petagram of carbon equals 3.7 gigatons of CO2. So if you're used to hearing numbers of CO2 fluxes, I'm always talking about just the carbon, not the weight of the whole atom or of the whole molecule, but just the carbon atom. And that's also what we see in this graph here. So this graph represents the global carbon cycle. This graph is actually quite a few years old now. I like this layout a lot better than what they changed to later on. So it's from NASA, but so I still use a slightly older one. So you can see, for instance, now in reality, the atmosphere is actually closer to 900 than 800, etc. But what we see in this graph is different components of the active part of the carbon cycle mainly. We see stocks of carbon or storage of carbon in white numbers. We see fluxes or flows of carbon in yellow numbers. And then we also have a few numbers that are in red, which are the numbers that are caused by human activity. So we see human emissions here of 9 or 10 gigatons of carbon. We see photosynthesis, as you know, a major flux of carbon into the ecosystems. And then we see how this can move into soil carbon, which is really the largest reactive pool in the global carbon cycle. We have even more carbon perhaps in fossil carbon or in sediments, but on land, the largest responsive reactive pool of carbon that turns over at annual or decadal timescales is really in the soil. So in this graph, this is estimated to 2,300 gigatons of carbon, which is almost 3 times as much as what's in the atmosphere. Newer estimates are closer to 3,000 actually, so this number keeps going up. And a very large part of this carbon is stored in the permafrost region in Arctic and boreal biomes. So when we see the photosynthesis, we see the respiration from plants and from soils, and it's sort of this part of the carbon cycle that we're going to focus on mainly today. There's also a lot, of course, that happens in the oceans, with turnover in the oceans. I'm not going to talk so much about that. One important aspect of the Earth system is that it does us the favor of absorbing roughly half of the carbon that we emit to the atmosphere. Now I'm going to go back to the carbon cycle again, so to sort of point that out. We have these numbers that are 120 plus 3 and 90 plus 2 in red. And what this shows us is the added carbon that is being taken up via photosynthesis on land and in the ocean, also through just air-sea gas exchange, because we are making more CO2 into the atmosphere. That also makes the ecosystems a little bit more effective in absorbing that CO2. So roughly half of the CO2 that we emit is taken up again by the ecosystems. And if we look at these natural sinks, they are projected to actually change depending on human emissions. So if we go with low emission scenarios, the land and the ocean is able to absorb as much as 70% of what we have emitted. But if we go to really high emission scenarios, these natural sinks of the Earth system, they basically become saturated. There's only so much that land and ocean can absorb. Even if the total absorbed CO2 in land and ocean is higher in these scenarios, the Earth can only absorb around between 30 and 40% if we go to really high emission scenarios. So the sort of natural dampening effect of the Earth is also limited in how much it can absorb. And there are also, of course, negative effects of some of this like the ocean uptake, for instance, partly leads to ocean acidification, which is extremely damaging to oceanic ecosystems. So these sinks don't come completely free either. They also come at the cost for biodiversity and other aspects of the Earth system. So this means that we are right now really relying on these natural sinks to help us buffer emissions, and that to a much smaller degree we will be able to keep relying on the Earth system to help us in this context as we move into the future. And one important aspect of these natural sinks and the weakening of the natural sinks is the potential future emissions and ongoing emissions from the permafrost region that will actually probably even further reduce the ability of the Earth system to absorb our emission, because we will actually start getting feedback that are so strong that it will really start releasing ancient CO2 into the atmosphere and methane. But I want to start by just mentioning some of these carbon cycle feedbacks that exist in the global carbon cycle that are included in Earth system models. A lot of these processes are included in the dynamic climate models or Earth system models. And the most important ones that are, that models can simulate is then the land carbon response to CO2 and the ocean carbon response to CO2, which are these extra 3 and 2 petagrams that I showed you in the carbon cycle graph. So basically what this means is that because there's more CO2 in the atmosphere, the plants grow better, and you actually get the cooling feedback because the plants take up some of this. And the same for the oceans. There's higher primary productivity, and there's also a higher gas exchange into the oceans, which means that there's this cooling feedback. And this is due to the CO2 concentration alone. But the actual warming of the climate, so the fact that the temperature is getting warmer, still gives us a positive or a warming feedback on climate. So you actually have to separate the effect of the carbon dioxide itself and the climate warming caused by the carbon dioxide. So those are two different things. But these are feedbacks that are then included in the models. And just again, we see them here in the carbon cycle as a +3 and a +2 in this case. But there are also a lot of carbon cycle climate feedbacks that are missing in our system models. And this now refers to the models that we use in the last IPCC assessment. And this is from the last IPCC report, Working Group 1, and here they show the strongest missing feedbacks. And these are then fire emission or fire CO2 emissions in response to climate, permafrost CO2 emissions in response to climate, permafrost methane emissions in response to climate, and wetland methane emissions in response to climate. So most coupled climate models used by the IPCC do not have these processes in them, which means that they are not fully included in the model estimates. But the IPCC panel made separate estimates of how large these feedbacks are, which you see here in this graph, and accounted for them when they tried to sort of calculate our remaining emission budgets. And if we take this together, all of these feedbacks together, they equal roughly 5-10% of the total human change in radiative forcing that we have imposed on the Earth system. So it's not as much as we are emitting, but the numbers are quite high. So annually, it amounts to this, which means that these feedbacks are really critical to sort of really be able to close the loop and understand the full Earth system. So I'm going to focus specifically on the permafrost carbon feedback. which was discussed by the IPCC and partly included, but perhaps not fully, as you will see that in the sort of remainder of my talk. And permafrost is permanently frozen ground in high latitudes, most prevalent in Arctic, but actually also in boreal ecosystems. More than half of the permafrost region is covered by boreal forest, even if we often think of it as tundra, but a lot of it is actually under forest. So you have ground that is frozen all year round, and this ground is characterized not just by a lot of organic material and soil, but also by a lot of pure ice in the ground. And when it thaws, you can get quite dramatic effects on ecosystems and also on the global climate. This image shows a site in northern Canada, which is where you see a very dramatic landform. So I sort of like it because it represents the scale of this problem. It's a massive, it's a very large area that has large effects or potential effects on the global climate, but also rather sort of slow acting effects. So you can view it as one of the sort of sleeping giants of the global carbon cycle. But what happens is basically, we talk about the permafrost carbon feedback, is that global warming leads to increased thaw of permafrost. And because this permafrost stores a lot of carbon, old plant remains mainly, when it's thawed, it's remobilized, becomes available for microbes to start to eat up these old plant remains. And as a byproduct of their consumption of organic matter, they release either CO2 or methane as part of this respiration. And then that releases them further greenhouse gases into the atmosphere, which causes a reinforcing loop because you get further warming. There are also a lot of direct impacts to ecosystems, to infrastructure, and humans living in the Arctic. I'm not going to go so much into this in this talk. I'm going to talk mainly about the global consequences, but I think the direct effects are most strongly and keenly felt by the people that live in the Arctic, and of course, direct impacts to the ecosystems. So see the difference before and after thaw can be massive, and that obviously affects plants and animal life and human life directly in the Arctic as well. So this graph shows us the simulated extent of permafrost in 2003, and if I start this movie, hopefully you will see model-based evolution of near-surface permafrost from 2003 to 2017. This data comes from a European Space Agency project that I'm one of many contributors to, and it's a model that is driven by satellite remote sensing. So we have satellites that observe the actual ground surface temperature, and then we use that together with a lot of other data to drive this model. And you can see that the extent diminished quite a lot in the early 2000s, and then it has stabilized a little bit. But it is a very large area that we're talking about. Permafrost affects roughly 20% of the land surface in the northern hemisphere, and it's most prevalent in Siberia, of course in Russia, but then also in Canada, Alaska. We have a little bit of permafrost in northern Fennoscandia as well, as you see in this map. But we are not only concerned with, so we have this warming and thawing of permafrost that mainly affects the southern edges of the permafrost. You can think of the permafrost as sort of creeping northwards along the southern edge. But there's actually emerging evidence, and very alarming evidence, that the permafrost is warming everywhere. So even in super cold areas where we have what we call continuous permafrost that is covering the whole landscape, the rate of warming is actually the highest. So we are seeing effects also in the really far north, which should still remain frozen for decades or centuries, according to model estimates. So this is the observed subsurface temperature changed or modeled / observed. It's a mix of model and observation results from 1997 to 2019, and we see that there's been a massive warming of the permafrost, particularly in northern Siberia. And there are many different reasons for this. It's warming, it's links to sea ice extent, it's coupled to snow distribution patterns, etc. So there are a lot of factors that come together and give us this pattern. But this means that we're seeing changes also in this northern permafrost at a very high rate. And this is a concern then because of the massive size of the permafrost carbon pool that is then reactive to be decomposed and potentially be emitted into the atmosphere. in this figure, we see the sizes of these bubbles are proportional to the sizes of these carbon pools in the Earth system. So you see the atmosphere at almost 900 gigatons of carbon. We have vegetation. All vegetation on Earth is roughly 500, and all the soils in this case is updated to more than 3,000. But here we see then the permafrost, the orange part, the permafrost region, even though it's only 20% or 15% of the global land surface, it's a really massive storage of carbon. So even if only a few percent of this carbon pool gets remobilized into the atmosphere, it makes a very big difference to the climate. But as I mentioned earlier, the IPCC did try to account for this in the last report, and they made not model-based but literature-based estimates, but they were quite cautious estimates. But still, it was a great stride forward that they made these estimates, and they estimate. And now I'm changing actually to gigatons of CO2 rather than gigatons of carbon, because that's what the units IPCC used. So we see the gigatons of CO2 that they project will be emitted from permafrost by the end of this century, under different global warming scenarios, 1.5, 2, or 4. And then we see that we are around 150 gigatons and increasing quite a lot, even if we come to a 4-degree warming scenario. And for reference, you have on the right-hand side here of the graph, you see the remaining carbon budget to stay below 1.5 degrees. So it's we are reaching under the 4-degree warming scenario, reaching almost half of the budget that we have left to stay below 1.5 degrees. It's important to note when I make this comparison of permafrost emissions versus the 1.5 degree budget is that they are relevant. I think the comparison is relevant, but they are acting at different timescales. Here we're talking the permafrost emissions would be to the end of this century, and they would go on for hundreds of years after that, while the remaining carbon budget to stay below 1.5 degrees is something that will reach in a matter of 5, 6, 7, 10 years, depending on human emissions. So they are, they are the same scale, but they are happening at different time horizons. But one thing that wasn't fully accounted for by the IPCC is what we group together as calling them abrupt thaw processes, or thermokarst sometimes. And these are processes that cause irreversible change to the permafrost zone, and they are associated with massive ground ice. So in a lot of places in the permafrost region, you will have enormous amounts of pure ice in the ground. In this photograph here, you see some scientists that are looking at the upper part of an ice wedge in Siberia. And this ice wedge is roughly 10 meters wide and about 30 meters deep. It's really massive. We don't see all of it in the photo, of course. But in these areas, up to 70% of the whole volume of the ground is made up of pure ice. And you can imagine when that ice melts and drains away, you will get massive changes to the landscape. So abrupt thaw processes over time give us this change as where the ice volume disappears, you have a gradual lowering of the ground surface, and then the post-thaw ecosystem looks fundamentally different from the pre-thaw ecosystem. You can go from a dry and flat tundra to lakes, and you have a completely different system, which is also associated with usually very high emissions of methane after thaw, because in these wet post-thaw environments, the microbes produce quite a lot of methane. And if we account for these processes fully, which was not really accounted for by the IPCC, we see that our emission scenarios go up even higher. So that they increase substantially, especially in the 4-degree scenario. So this adds up to even more massive emissions potentially in the future from permafrost. Another complication which has not been accounted for fully is the effect of what we call overshoot warming on permafrost and other Earth system components. Overshoot warming is the sort of potential future scenarios where we will shoot over our target temperature and then go back down to the target temperature later on with some sort of negative emission technologies. So there are different ways for us to reach our target temperatures. Ideally, we would just want to cut emissions rapidly and then stabilize at the target temperature or even go down. But in overshoot scenarios, we go over and then we go back down to say 1.5 or 2 degrees. And the argument for doing an overshoot scenario would be that some people might argue that climate solutions or negative emission solutions to suck CO2 out of the atmosphere will become cheaper in the future. So it makes sense for us to keep emitting now, and then we just put it back down later, and then we save money, which is probably not the case. But there are two problems associated with overshoot scenarios for permafrost. The first problem is that because we have this feedback, the warming will be even higher. So we will shoot over even higher because the permafrost feedback will add additional CO2 and methane to the atmosphere. And that will even cause an overshoot in the sort of green scenario here. And the second big problem here is that a lot of the permafrost loss, once it has occurred, so the thawing that happens when we're in this hump of warming here, will be irreversible. Even if we cool the system back down, a lot of the permafrost is going to stay thawed and it's going to keep emitting for hundreds of years. So if we add overshoot to the future predicted emissions, this is based on a model study where we compare no overshoot, a little bit of overshoot, and a full degree of overshoot. That adds significant additional emissions to this scenario. So now we're only looking at 1.5 and 2 degrees here. Note. So the sort of gathered picture of taking it together is that with abrupt thaw and overshoot added to the mix, the permafrost emissions may be very high. Another very important aspect of permafrost, or the properties of permafrost, is that it responds really slowly. So in these scenarios that I've been showing you, these graphs, we've been looking at the different scenarios where we cap global warming to 1.5 or 2 or 4 degrees by year 2100. But even if we stop warming there and would somehow magically completely stop emitting CO2 at 2100 and stay at 1.5 or 2, the permafrost that is thawed by then will keep emitting CO2 and methane for several more centuries. And this is because of the properties of the landscape, and especially this abrupt thaw landforms that you have. Once you've gone from the dry tundra to a wet lake or a wet peatland, it's not going to just refreeze or stabilize. It will stay wet and it will stay thawed for a long time, and it will keep emitting for a long time. So this essentially means that even if we stop warming, several hundred gigatons of CO2 or carbon will still flow into the atmosphere from the permafrost up until 2300 or possibly beyond. And this in turn has, of course, long-term consequences for coming generations of humanity that we essentially force several future generations to have to deal with permafrost emissions. Even if human emissions were stopped, the permafrost would keep emitting, so we would have to keep implementing negative emission technologies for several hundred years just to cope with the permafrost emissions, the damages to the permafrost system that we invoke now. So on that topic, so this is material from the working group one of the last IPCC report, where they have a section on frequently asked questions, which I think is quite nice. And one of the really pertinent questions there is that, well, could climate change be reversed by removing carbon dioxide from the atmosphere? And they use this scenario here as an example of, to answer that question, where you see atmospheric CO2 concentrations in ppm over time. So here they have a theoretical peak somewhere around 2070, and then it goes down again quite rapidly. And then the question is, what happens to the Earth system under these changes? And they conclude that, for instance, if you look at global surface temperature, you can actually reverse it. But there's a lag time of years, and you see here at a slightly higher elevation. So this is a scenario that lands at 1.5 degrees, but overshoots up to 2.5 degrees. But temperature can be reversed. Some other aspects of the Earth system, the IPCC, yes, it's reversible again, but there's a lag time of, in this case, they say decades. I think that decades is too short, actually. I think it's more like centuries, because the sort of bounce back of permafrost is unlikely to be this fast. I think the models overestimate how fast the ground refreezes. But still, it's partly reversible with the lag time. And then there are other parts of the Earth system that are basically irreversible. For instance, ocean thermal expansion shown here, it's reversible over several millennia, many thousand years before it bounces back. Ocean acidification is another example of something that's essentially irreversible, and there are also indications that ice sheet dynamics in Antarctica and potentially also Greenland might have built-in thresholds, which means that once we pass the threshold, that will also actually be a largely irreversible loss, or at least a regrowth that will not happen for very, very long time scales. But then another thing that is really important to point out here is that, okay, so the IPCC says that permafrost loss is partly reversible, but there's also important to note this very large shift in permafrost area. So even in this reversible scenario, we've actually lost what we have on this graph or on this axis here is millions of square kilometers. So we would have lost 5 or 6 million square kilometers of permafrost, which would store several hundred gigatons of carbon that would keep emitting CO2 and methane to the atmosphere for several hundred years. And it will also affect, of course, the population living on that permafrost. So this is my last slide, just summing up permafrost thaw and its impact. We have recent evidence suggesting that the permafrost region is actually already a net source of greenhouse gases to the atmosphere. If you combine CO2, nitrous oxide, and methane, it's already a net warming. And regardless of trajectories that we take now, we are already committed to profound permafrost thaw impacts that will decrease remaining emission budgets and affect several future generations. The question is just how much. There's also very good scientific support for the occurrence and acceleration of so-called abrupt thaw process or thermokarst that will create local scale irreversible tipping points in the ecosystems, which is basically something that after you have passed this threshold of the ice disappearing and the ground collapsing, it will take a very long time for these ecosystems to recover. And it also leads to a lot of infrastructure damage affecting people living in the Arctic, and it greatly increases warming. And we also find clearly evidence that overshoot warming would trigger irreversible permafrost thaw that drives additional warming for several centuries, even after the climate stabilizes. So that was all I had to say. Thank you all for listening.